Welcome back. Let's get started with this talk. So it's great to have Surjeet Rajendran, who is a recipient of the Frontiers of Science Awards this year, and she'll tell us about cosmological relaxation.
Great. Thank you very much. It's been a lot of fun for me to be here at this lovely conference, talking to so many interesting people, not just in physics, but also computer science and mathematics, which is always very exciting. So I'm going to speak about this work for which we won the FSA. But I'm going to not just talk about that paper, but also talk about some series of ideas that have come out of that and some continuing thoughts. Okay. So presumably everybody here knows this, but since I'm supposed to provide introductory material, I will still say it. So our motivations is to talk about two of the important hierarchy problems in particle physics. And these are tied to very obvious facts about the world. Fact number one, gravity is very weak. I can lift an object trivially off the ground, even though the gravity of the entire Earth is pulling down on it. And second, I can see far into the universe. And that is because light from distant objects can get to us. Why do these things happen? Well, that's because if you take the force of gravity between two protons and compare that to the force of electricity, that ratio is something like 10 to the minus 38, which is why the electrical forces in my hand can trivially overcome the force of the gravity of the entire Earth. And the reason why I can see far into the universe is precisely because as light from far away comes towards us, you know that the expansion rate of the universe is slow enough that the light doesn't get too diluted. And that is fundamentally because the energy density in the universe is pretty small. So the question you might ask is basically, why are these numbers so small? One attitude you could take to that is basically there's an explicit small parameter in the theories of nature. So just be happy that you can lift objects and you can see far. That would be perfectly fine. But of course, the problem is in quantum field theory, we have a sharp version of this problem, which is that you can make estimates for what these parameters ought to be. And as we all know, or presumably most of us know, that we find that the theory predictions and the observational numbers are dramatically off. So it is this extreme fine-tuning that we want to understand, right? Why is the theory number so dramatically different from the observed value? So the current approach that people have pursued for, say, the hierarchy problem, which has to do with the mass of the Higgs, is that we propose the existence of new particles, and we want these new particles to have some kind of symmetry structure so that the contributions from the known particles almost exactly cancels the contributions from the new particles. And we get a very small mass of the Higgs at the end of the day. And the problem with this approach is that, indeed, today, because of the LHC, we have ruled out pretty much all of these approaches. So that level, this problem is now very similar to the cosmological constant. Because you might have thought that you could invoke the existence of new particles, which would cancel the contributions to the vacuum energy. And indeed, if such a solution had been true for the cosmological constant, you would have ruled out that solution in something like, 4000 BC, when we first began cooking food, right? Because if you had a new set of particles at the milli-eV scale, every time you cook food, you're actually producing EVs of energy due to chemistry. And the fact that when you cook food, you get what you expect to get as opposed to new particles is telling you that, well, there aren't few degrees of freedom at the milli-eV scale that are solving the cosmological constant. Okay? So broadly speaking, I would say that today, both the hierarchy problem and the cosmological constant problem, at least in my opinion, are the same situation where new degrees of freedom are not coming in and solving those problems. So the question that we have been asking ourselves is there a strategy that we can actually invoke that would solve both these problems simultaneously, right? That's kind of our idea. And the motivation here is to say that, well, we traditionally don't think of time evolution as being all that important in physics, but maybe we should think about time evolution as being important. So I would argue that time evolution can and should change your expectation of what's natural. So for example, if you thought about the infant Earth and you wandered around the infant Earth, you might see coastlines like this, very, very rocky surfaces with water right next to it. That would be your expectation of what is natural in the infant Earth when the Earth was very young. Whereas if you now wait for billions of years, what you typically expect is that there would be lots of erosion, which would have converted this very, very rocky coastline into something very nice and sandy, so we can go and have nice vacations, right? So your idea of what is natural in the world clearly depends upon how old the world is. So could something like this also be true in the cosmos, where we would basically say, is it possible perhaps that the Higgs mass and the cosmological constant may have been dramatically different in the early universe, and over the course of time, they have eroded away and become something small today, right? Is that possible? And indeed, I am a physicist, which means that I would like to test these theories. That's an important part of doing physics. So we have to ask if indeed these dramatic things happen in the early universe we live today, what would we have to do observationally to go and test these kinds of ideas? So that's the outline of the talk. I'm going to tell you broadly thoughts we have on the relaxation into naturalness, if you will. So I'll first start talking about the hierarchy problem, and then we'll talk about what one can potentially do to the cosmological constant, and then I'll very briefly mention what you might be able to do experimentally. The gauge hierarchy problem. Okay, so what do we want, right? We want a situation where we say the Higgs mass is fundamentally something extremely big in the early universe, and over the aeons of time it's changing. So if you want to put that in your model, if you want to create dynamics of this kind, what do? You basically say, look, I'm going to have a large mass of the Higgs fundamentally, this mu squared Higgs squared, that's some large mass of the Higgs. Mu is something that's much bigger than the weak scale. That's roughly what you start from. And then you basically say, I want some technology that will allow me to change the Higgs mass over the aeons of time. And the simplest way to do that is by having a scalar field. And I'm going to have the scalar field roll over the course of the universe. And when that happens, the physical mass of the Higgs, which is the sum of these two things, will change. And that's what we will empirically measure. That's the idea. So what do you want? You want something of this kind, where you have a scalar field that's rolling over the course of time. As it rolls, the physical Higgs mass is changing. And ultimately, you want to get to a point where the Higgs mass square becomes the number that you want. And at that point, the Higgs mass has to stop changing, right? So what you want is to basically say the scalar field keeps rolling, and when the Higgs mass becomes the value you desire it to have, some barriers show up for the potential of phi, and that's where the Higgs mass gets stuck. That's what you need to do. So if you're an engineer of some kind and you want to say, well, what kind of technology do I really need to create this particular phenomenon? Here's what you need, right? You have to basically be able to somehow sense that the Higgs mass goes from positive to the desired value that you want. So you need a sensor of some kind over there. So these are the three ingredients you need, right? You need some mechanism that scans for the values of the Higgs, and then you need something in your physics that senses the fact that the Higgs has hit the desired value you want it to have, and then you need to have some kind of mechanism or a back reaction that prevents the field from rolling anymore. So if you're able to engineer these three things, you have basically come up with a way to solve the hierarchy problem through time evolution. And of course, all this occurs in a background cosmology. So you need to take into account that also. All right, this is the simplest model that we wrote down, which I think most of you probably do know at this point. So what did we propose? We simply said, look, take the standard model, and to the standard model, add to it the QCD axion. So the standard model is the usual stuff. And if I give this phi, that's my QCD axion here, it couples to the gluons of QCD. So I turn that coupling on, okay? So that's the standard model and the QCD axion. What makes it the relaxion is the fact that I couple the scalar field phi to the Higgs mass squared over here, to this coupling G phi Higgs squared. And G is a technically natural small parameter here. And then I'm going to basically, once I write that coupling, I'm going to turn on all possible interactions that are radiatively generated by this coupling. So you get, various things that you get. They're all proportional to G. That's the main. Okay. And then we assume all of this is going to happen during a period of inflation in the early universe. So all this is occurring way back in the history of time, not today, obviously. And we're assuming there's a period of inflation where this field phi is rolling. So if I just give you this particular Lagrangian and I have a background inflationary scenario, let's see what happens to the physics. Well, initially, I'm going to assume that the value of phi is such that the sum of these two quantities is net positive. It's positive and very big, right? It's at the scale mu, where that's a cutoff of the theory, much bigger than the weak scale. So the very, very early universe, inflation is going on. The Higgs mass square is extremely big, very, very large. So what's happening now is that the scalar field phi will roll. As the scalar field phi rolls, what's going to happen is that the physical mass of the Higgs will keep changing, okay? And eventually, the physical mass of the Higgs will cross zero, all right? It's going to go from being slightly positive to slightly negative. And at that point, I would like these barriers to show up that prevents the Higgs mass from continuing to roll. That's very natural in this model because there is a natural sensor for this to happen. which is the fact that as the Higgs mass square goes from positive to negative, you now see that electroweak symmetry is broken. That means the Higgs gets a Vev. When the Higgs gets a Vev, the quarks in the standard model acquire a mass, and when the quarks in the standard model acquire a mass, the axion automatically picks up a potential, right? So in this very simple model, we have actually achieved all the things that we required, which is that I need a sensor that tells me when the Higgs acquires the value I wanted to acquire, and the moment I have sensed the fact that the Higgs has acquired that value, I'm able to generate a potential for the axion and stop it from rolling. Okay, that's the simplest version of the story. What interests me about this particular scenario is not so much the specific model that we wrote down. People can go and complain about this aspect of the model and that aspect of the model. Fine, complaints are good. If you want to work on it, make the models better. For me, what's most interesting about it is basically what are the fundamental physical principles that this kind of model needs to have to be able to solve the hierarchy problem, right? So any model that has these fundamental principles will be able to solve this. So here are the fundamental principles that you need in order to solve the hierarchy problem in this particular manner, okay? The first very important one you need to have is that your mechanism needs to be dissipative, okay? And why is that? So if you think about it, I am starting initially where the Higgs mass square is large and positive. It's some very, very large value. That means the scalar field phi has a very, very large potential energy. The potential energy density is close to the cutoff scale mu. It's very, very big. And then as the field phi rolls, okay, if there is no dissipation in the problem, as the field phi rolls, the potential energy of that field will convert into kinetic energy, okay? And so as the field is rolling, it's got a large kinetic energy. And now as it crosses zero, which of course it will, these little barriers will start showing up, okay? But notice that the barriers, of course, depend upon the extremely small mass of the Higgs as it goes from positive to negative. So those barriers are going to be very tiny compared to the kinetic energy of the scalar field phi. So if that is the case, these barriers will not be able to stop the rolling of phi. Not possible. So if you want this mechanism to actually work, what you really need is that there has to be some source of dissipation which removes the kinetic energy in the field. So as the field rolls, the kinetic energy has to go somewhere. So the simple model that we wrote down with inflation is just the expansion of the universe that basically converts that kinetic energy and dissipates it away. So that basically means that as the field rolls down here, its kinetic energy is very, very small, so that the little barriers that we are popping up actually prevents the field from rolling. So dissipation is central. Okay. The second part of the story that's very important is self-similarity. So this is because of the fact that one can come up with a similar Weinberg-no-go theorem, which we will talk about shortly for the cosmological constant. But we can see a version of the Weinberg-no-go theorem for the Higgs as well. So what is the big deal here? So here is the big deal, right? If you look at this particular potential that I wrote down, this parameter mu that I have, that is coming from all the standard quantum loops that you're calculating, right? It's some totally random parameter that doesn't know anything at all about the scalar field phi. It's some completely random mu. Given this completely random value of mu, there is going to be a value of phi where these two things cancel each other. That's of course mathematically true. Now if your scalar field phi had only a small number of minima, then you want this totally random value of the field where these two things cancel, right? Whatever, call it phi naught. That random value of phi naught would have to be a minimum for the scalar field phi. Otherwise, the field cannot get stuck there. So if you had a field that only had a small number of minima, without fine-tuning, you cannot actually arrange for the minimum to land exactly where this quantity gets cancelled. Okay, so essentially the guts of Weinberg's no-go theorem, which again we will see shortly when I talk about the cosmological constant. So to tackle that problem, you require a field of some physical quantity, this scalar field phi. It must have a very, very large number of minima. Okay, so it must be a field that is capable of having a very, very large number of minima, and the periodic axion is a natural such candidate, because an axion is a field where you can easily have it you can easily give it a very, very large number of minima. Okay, and that's basically why. So if your field has a very, very large number of minima, then indeed it's not too difficult for you to find a minimum close to where this thing cancels. Okay, so that's important. The other part of the story that's very important is also that as you go through the point that you care about, right, when the Higgs mass square, for example, goes from positive to negative, we're able to create some kind of back reaction, and that is the important point here, which is the fact that if you think about it, right, why was it so difficult to solve the hierarchy problem in the first place? That is because you actually think about the mass square of the Higgs. The Higgs mass square being 0 is not a point of enhanced symmetry, right? Because whether the Higgs mass square is positive or negative or whatever it is, or 0, there is no enhanced symmetry in the theory. That's why it's very hard to come up with a symmetry-based solution to the hierarchy problem. However, the Higgs mass square being positive or negative is a point of importance for dynamics. Because when the Higgs mass square is positive, the Higgs has no wave. When the Higgs mass square is negative, the Higgs does have a wave. So if you're thinking about a dynamical solution, what you realize is that Higgs mass square being very small is a point of interest for dynamics. Okay? And that's exactly what we are making use of over here, where we basically say when the Higgs mass square goes from being positive to negative, electroweak symmetry breaks, and the breaking of electroweak symmetry can be used to trigger some kind of a back reaction that allows you to stop the motion of the scalar field phi. So that's another important point as well. And finally, all of this has to happen during some background cosmology, and in our simple example, we just use inflation. Okay? So indeed, so as long as you can put together all of these criteria in whatever model you want to write down, you will be able to find some kind of solution to the hierarchy problem using this kind of relaxation style idea. Okay? But this is an old story, and I think many of you probably are familiar with it. So let me move to the cosmological constant, right? That's the big one. So after all, why work so hard to solve the hierarchy problem if you cannot solve the cosmological constant problem, right? Since I would say both of them are in the same, game at this point. Okay. Yeah. Pardon? Yeah. I mean, not really. I mean, so I would say that, people have thought about models like clockwork, axion, etc., where you essentially just have a field with a very, very long period, right? So if you are concerned about that, I think one can indeed find ways to UV complete it. Yeah. Yeah. Well, it's now a question of how, I guess, long that period is. It's a question of how long that period really is, right? Yeah. Oh, you're saying I'm breaking this in some way. That's what you're saying, I think. Not necessarily, right? It's a question of, I think you're asking what is the UV completion of the model, and it's true that I'm explicitly breaking that. I'm breaking that shift symmetry. That's true, right? By putting in this G phi parameter. So it is not, in that sense, a fundamentally periodic field. That's true. Okay, that's true. Yeah. No. It's a fair question, and I think that's a fair question, but yeah, it doesn't bother me per se. All right. So let's try to solve the cosmological constant. Okay. What are we going to do? I'll tell you the story first, and then we'll talk about why every ingredient of the story is important. So I have a large positive cosmological constant. Let's start with that, lambda to the fourth, much bigger than the milli-eV scale. And then I'm going to give it a scalar field phi, okay, that couples like so, lambda to the fourth minus g cubed phi. So in the very, very early universe, I'm going to start with this large positive cosmological constant, and there's a slowly rolling scalar field phi. When that happens, of course, the universe is undergoing inflation. Okay, that's what inflation really is. And as the scalar field phi keeps rolling, the vacuum energy will keep changing. That will just naturally happen. Eventually, in this particular model, the vacuum energy will get very, very small. The universe will get very, very cold. And eventually, it is in fact true in this model that as the scalar field goes over here, the vacuum energy will go from being slightly positive to becoming slightly negative. Okay? At that point, something interesting happens because the scalar field, as it rolls over from positive cosmological constant to negative cosmological constant, it will acquire some kinetic energy. And because the universe now has a negative cosmological constant, it will start shrinking. It will start crunching. As it crunches, the universe will get hot. As in the kinetic energy of the scalar field will get very, very big, but notice that the cosmological constant is still small. At this point, if by some mechanism you can make the universe bounce. A bounce means there's a universe that is shrinking, it gets to some size and then starts re-expanding again. Okay? If you're able to create a bounce of this kind, then you're done, because what you end up getting now is an expanding universe, which will be hot, because there's a lot of blue shifting the kinetic energy, and the vacuum energy is extremely small. Right? So if you could make all of this work, you have solved the cosmological constant problem. And let me point out an important aspect of this particular story, because in this particular mechanism, what we are really doing is that we have factorized the cosmological constant problem into two pieces. One, there's an infrared part, and then there is a new physics that I'm going to invoke for the bounce itself. Why is this important? Suppose you meet one of these string theory guys or whoever who comes and tells you, look, I'm going to think about some new physics at the string scale to solve the cosmological constant problem. I would have said, look, this guy doesn't know what he's talking about, because the cosmological constant problem is a problem at the milli-eV scale. There is no point invoking physics at the Planck scale to try to solve the problem at the milli-eV scale. Right? That's a naive thing you would say. But in this way of doing business, what you are learning is that there's an infrared piece. That is a scalar field that is sort of rolling over the aeons of time. And that is doing the hard part. It is actually doing the actual scanning of the CC, making it very, very small. And all I need here is the fact that as the universe gets extremely dense, I can invoke new physics at the Planck scale or whatever, whose sole purpose is to make it bounce. Okay, to take a contracting universe and make it re-expand. So you can now you can invoke new physics at high energy, okay, to help you solve the CC, which is something that you cannot normally do. That's an interesting aspect of the story. And in our particular picture here, because of the certain mechanics of the actual model, it'll turn out that the initial phase, where the universe spends a very long time inflating and making the cosmological constant very, very small, that lasts about 10 to the 40 years, which in the United States now we call it as one Biden age. And the last 10 billion years is basically over here. Right? This is where we live. All right. So why do I need all these ingredients in my model? Okay, can I get away with anything? So I'm going to basically talk about that aspect of the story, why everything that I said in the previous slide, this entire picture, is necessary if you want to solve the cosmological constant problem using relaxation ideas. And then I will talk about this bouncing universe. Is that something that's possible? What can you do about it? Why is every ingredient necessary? Well, here's why you need every aspect of the story, right? What I want to do is I need to have some physics that senses the value of the vacuum energy, and then when the vacuum energy hits the right value, I need to, stop it, right? That's what you need to do for a Relaxation mechanism, which means I need some kind of a sensor for the vacuum energy. The problem is the vacuum energy only couples through gravity. And gravity, of course, is universal. So gravity couples to the total energy in the universe. It cannot distinguish between individual components. So if you ever try to solve the cosmological constant problem during the hot early universe, you cannot do it, because gravity cannot sense the vacuum energy alone. It only senses everything. So the only time you can be sensitive to the vacuum energy through gravity is when the vacuum energy dominates. Okay? And that means the only time you can solve the cosmological constant problem is during a period of inflation. You cannot do it otherwise. Second, why do I need this bounce? Okay. Well, what's happening here is that I have a large cosmological constant, and my scalar field, as it rolls, the vacuum energy slowly decreases. Okay. Now, this whole bounce business is because of a quantitative aspect of the cosmological constant problem. Suppose the cosmological constant problem had been that you had to decrease the vacuum energy from something very, very big, let us say, Planck scale or whatever, down to, let's say, GeV to the fourth. You don't need a bounce, okay? We wrote down models where you can actually trivially take a very large cosmological constant and bring it down to, let's say, GeV to the fourth. No problem. You don't need a bounce for that. The reason why you need a bounce is because of the numerical fact that the actual cosmological constant in our world is a milli-eV. Okay, or milli-eV to the fourth, around 10 to the minus 12 eV to the fourth. That's a physical fact about the world. So that means I need to have this inflation running for such a long time that the CC eventually gets down to 10 to the minus 12 eV to the fourth. Okay? And remember, I'm inflating at this very, very low cosmological constant, and that means every other energy density needs to be smaller than milli eV to the fourth. Okay? It has to be smaller than that. But our problem is that we know that 10 billion years ago, our universe had radiation with a density of around capital MeV to the fourth, 10 to the 24 eV to the fourth, right? So if you're trying to use this entire mechanism to solve the CC problem is you have to decrease the vacuum energy down to a milli eV to the fourth, and then somehow you have to reheat the universe up to capital MeV to the fourth. That means it looks like you need to violate the conservation of energy. Now, the only known, experimentally verified, and theoretically consistent way of violating the conservation of energy is through gravity. Gravity does not have a conserved energy. Okay? So that's trivially what we're doing, is that we're saying as the scalar field rolls through zero, the vacuum energy is going to go from positive to negative. There will be a kinetic energy for the scalar field phi, and now as the universe is shrinking, the energy density in the scalar field will blue shift dramatically. That just naturally happens. And that means your energy density will go up and up and up. Okay? So you can start with an extremely cold universe, and the moment it starts shrinking, the energy density has now gone up by a lot. So that's why you need that. So we have to make use of the fact that energy is not conserved in gravity. Why do I require this 10 to the 40 years of scanning? This enormous time. That explicitly in our model is because I put a very, very small g. Okay, this tiny, tiny little g over there. So that again is basically due to this Weinberg-no-go theorem, which we will see in this form here. So what was Weinberg's big deal? Weinberg's deal was the following. Look, I want to solve the cosmological constant problem, which basically means I need to cancel the large vacuum energy here. So this lambda is some totally random parameter, right? It depends upon all loops, this, that, some gigantic number. And there is some value of the scalar field phi naught where these two things will cancel. That's just true. What do I want? I want it to be the case that as phi goes through this particular point, okay, I want the scalar field to get stuck there, right? So that basically I'm at a minimum. Now, if your scalar field phi only had a small number of minima, how could you possibly arrange that both the potential, which is lambda to the fourth minus g cubed phi naught, that's the potential of phi, why should both the potential of phi as well as its minimum occur at the same point, right? If you had a field with a small number of minima, you can't really arrange those two things unless you fine tune. But what we do here is something very dumb. We basically say, look, if the coupling G is very, very small, then indeed as you go through zero, right, your cosmological constant will still keep changing, but the change is so tiny that it's perfectly okay. Because I live in the last 10 billion years, it's taken 10 to the 40 years for me to go from here to here. And that means if G is small enough, in this 10 billion years, the vacuum energy would not have changed very much, and that's perfectly fine. So that's why we need the small g. Okay? So that's how we get around Weinberg's no-go theorem. Let's talk about the bounce. Okay, so I've convinced you that I need the bounce for this to actually happen. Right? Now, bounces, okay, irrespective of our story, are independently motivated, right? Because indeed, if you think about it, even in our standard story, even if you had inflation, the initial singularity in our universe is not eliminated. So as you turn the clock back, you know that the energy density gets bigger and bigger and bigger, and eventually there comes a point where general relativity breaks down, right? So we all know that. Even with inflation, you don't remove it. And, this is one of those things where I have found reactions to this depends a lot on whether I am in the Western world or in the Eastern world, where, in Christendom, people have very strong opinions. They think the universe definitely started 10 billion years ago, whereas I grew up in India, I was raised Hindu, and for me, this idea that the universe could have existed forever in the cyclic way, where the universe expands and contracts, expands and contracts, expands and contracts, is philosophically very nice. Okay, and I have no problem with that. So, that joke aside, see, why is there this thing about bounces? You know, that's something that Paul Steinhardt talks about, nobody else talks about. Why is there all this sociology about bounces? Okay. Well, what's the problem with the bounce? The genetic problem you have is that you have a shrinking universe that needs to expand, right? That's what you need. So you require, in this particular space-time, you've got converging geodesics as the universe is shrinking and shrinking and shrinking, and then it needs to re-expand. Okay? And why is that problematic? Well, what you might say is the following, right? That basically, look, I've got this matter, okay? This matter is shrinking and shrinking, it's getting very, very dense, gravity is getting very, very strong, and as gravity gets very, very strong, if I now need to emerge from the strong gravity, that sounds wrong, because gravity is always attractive. How could it possibly take something that's convergent and make it re-expand? That sounds wrong, right? So our friends in the world of gravity, they spend a lot of time proving no-go theorems about how such a thing could never happen. Okay? Now let me make fun of them a little bit. So let's ask the following question. Can matter never escape strong gravity? Well, let's ask the following question. Let me take a bunch of matter and let me make it collapse. It'll form a black hole, for example. It forms a singularity, a black hole. And what Hawking showed was that if you believed that the matter just gets to strong gravity and remains in there forever and never gets out, Hawking showed that it was actually inconsistent, right? One way or another, we can argue about whether the matter eventually comes out through Hawking radiation or to something more violent like a firewall. That's a great discussion to actually have. But no matter what Hawking showed was that once matter gets a strong gravity, it can't just remain there, it needs to get out. So if you look at this particular picture, it's exactly what's happening here, right? You've got converging geodesics that go away, that become divergent, okay? Phenomenon that needs to happen. Fact number 2 is observational. We know we exist, no doubt about that, okay? You turn the clock back, you definitely get to a point of very high density, but general relativity breaks down, okay? Now we can think about what happens over there, okay, some new UV theory, whatever it is. The one certain fact about our world is that we emerged from that singularity. That means we got out of a very, very strong gravitational past. The problem with the bounce is not getting into one. It's very easy for a universe to collapse. What is difficult is emerging from a period of strong gravity. That's exactly why there's all this stuff about how that can't happen. But we all know that we got out singularity. Okay? Zero doubt about that as well. So for me, it's a matter of great amusement that these guys spend all this time coming up with theorems for how this cannot happen when it obviously does and did. Okay? Gives me an opportunity to think about it. All right. So I would say there's very little doubt in my mind that matter does escape from gravitational singularities. And a singular bounce, by singular I just mean a bounce that happens when GR breaks down, okay, is pretty clearly possible. And remember, my motivation for this entire picture was that when you think about this problem the way we are thinking about it, we have factorized the cosmological constant problem into an infrared and a UV piece. The infrared is where the scalar field rolls, does all this kind of stuff. And the UV is something else, right? That you can invoke new physics at the Planck scale, whatever it is, whose sole purpose is to cause the universe to bounce. As long as that happens, we have solved the cosmological constant problem. So all you really have to do in this scenario is to bet that in the UV, a bounce is possible. And I'm very happy to take that bet, given my own existence. But we want to be a little bit better than that. We want to ask, is it really even possible to have a non-singular bounce? Something that is even within the domain ability of general relativity. Is that possible? So let's try to quantify this particular story and see what we would need. So what do you really require for a set of converging geodesics to start diverging? Okay, so the GR guys will point to something called Ray-Choudhury's equation, which essentially tells you, look, I've got a converging congruence, as they call it. I need that guy to diverge. So this parameter, this d theta d lambda, right, that is basically telling you how these quantities are converging and then diverging. And so what you want is, when this guy is converging, this quantity is negative. When this guy is diverging, that guy becomes positive. So if you look at the terms over here, there are these two terms that are explicitly negative. This term is explicitly positive, and then you've got this particular term, T mu nu, U mu U nu. So the usual claim is that if you want this term to suddenly become positive now, you either require this term to be negative, and that is called the violation of the null energy condition, or you require this term, okay, to be non-zero. Now, there's a lot of difficulties in writing down sensible scalar field theories that violate the null energy condition, okay? And that is why there's all this question of can a bounce happen, not happen, blah, blah, blah. But you look at this, equation and you say, look, okay, maybe that's hard. Why not make use of vorticity? Okay, there's omega term. Okay, this omega not equal to 0 is called vorticity. What is vorticity? Well, what do you really need, right? So what you're talking about is that I'm converging, and I now need to start diverging. And that basically means I have to combat the attractive nature of gravity. So we do it every day. When we are going around the sun, we don't fall into the sun because rotational motion is able to fight off the attractive nature of gravity, right? We're not falling into the sun because we violate the null energy condition. We do so by just rotation. Okay, so that's a simple idea. That's what this term is about. You combat attractive gravity with centrifugal motion. So why not use this term? Okay, why don't the GR guys use this term? So the point is, right, if you want to produce a world like we live in, which is homogeneous and isotropic, okay, then you require this rotation to exist everywhere, right? That's the key challenge. I can always locally have rotation, but what we need to completely avoid null energy condition violation is that if I have an isotropic and homogeneous universe that needs to go through a bounce, there needs to be this rotation everywhere. You need global vorticity. In fact, there was a space-time of this kind that was conceived by Gödel, and the primary reason why Gödel wrote this universe, the Gödel universe as he called it, is to annoy Einstein. That was the sole purpose. Okay? So what was he trying to do? He constructed a space-time where every point was rotating around every point. So if you think about it, right, like in terms of homogeneity, when I think about expansion of space, right, I am expanding relative to Alessandro there, right? That's what's supposed to happen. Every point is expanding relative to every other point. So when you now think about a rotating universe, you would basically say that, look, every point is rotating around every other point. That's a homogeneous way of creating it, and this is a metric that actually realizes such a homogeneous rotation. Okay, and it turns out that the specific model that Gödel wrote down just had a positive cosmological constant and some spinning dust, and that wasn't a universe that was exponentially expanding or contracting, none of that stuff. Basically, in that particular universe, it was static. The universe didn't evolve in time, precisely because the gravity of the space-time was being exactly compensated by rotation. Why did Gödel write this? Gödel wrote this because this particular space-time has an interesting feature, which is if you take a particular point and far enough out, that point is also rotating around you, and you can compute the velocity, some omega r between where you are and a distant point. And if you go far enough out, omega r becomes bigger than 1, right? Which basically means that point, as far as you're concerned, will start moving back in time, right? Because you go far enough out, you're rotating so rapidly, okay, that your velocity, becomes much bigger than 1. So in this particular space-time, it turns out that you've got closed time-like curves everywhere. And so Gödel's whole point was to say, look, Einstein, in general relativity, the theory that if I just take a cosmological constant and some spinning dust, I lose all meaning of time, right? That was what Gödel was trying to get to. Look, I don't have strong opinions about closed time-like curves, but what I'll basically say is that this does not seem like the space-time that we live in, right? So you cannot really use Gödel's idea directly for what we want. So what we wanted to do was something a little bit different. We want to have global vorticity. We want to have vorticity everywhere, but we want to avoid these closed time-like curves. The key point, right, is that if you want to create these closed time-like curves, it only happens because distant points are rotating around you. That's why you get it. But to avoid the singularity, you just need to have rotation at every point. So what we imagined was, well, maybe, and this is the way we are different from what people thought about before, suppose the space-time wasn't just R4. Suppose the space-time was R4 cross a little torus, let's say T3. And as the universe is shrinking and getting very dense or whatever, could I have rotation just into the extra dimension? Okay, so at that point, every point in space, I'm going to rotate in the extra dimension as I get very compact. That would give me global vorticity at every point, but I'm only rotating into the compact extra space, so I'm not creating a global closed time-like curve. Okay, so this is a simple model that we wrote down. You can take some metric, okay, a squared that corresponds to r large dimensions, and then I have some extra dimension, theta, phi 1, phi 2, or whatever. Those parameterize the torus T3, and then these extra terms here those are the vorticity terms. Okay, this is very standard stuff that everybody knows about. Anybody play with extra dimensional models, that's exactly what you have. And this is the fact there's a rotation going on, that I've got this dt d phi 1, dt d phi 2 with the sine and cosine theta. That tells you that this allows geodesics to rotate into each other. Okay, and what we did is that you can now plug in for AFT, a bouncing metric that you want. You can then use Einstein's equations to end up getting the kind of stress tensor that you need to create, say, a bouncing universe. What we've actually shown is that it's actually possible to get a non-singular bounce without getting closed time-like curves, and the kind of matter that we need, okay, it's even something that we didn't write down on our paper, but we know now, is basically something very vanilla. It's like a positive tension brain gas. That's what you need, that is moving in the extra dimensions, that will actually allow you to create these kinds of bounces. So probably over time, I don't know, 5 minutes, yeah, okay, good. So anyway, that's a story that we landed on some years ago. But let me, in the last couple of minutes, just tell you about experimental tests one could actually do. I just only have one slide on this actually. So, and I'm an experimentally driven guy. The rest, if you can't test it, what's the point, right? So, how would you test a scenario like this? Well, let's go back and think about what was necessary in the case of, let's say, this coastline, right? So, if someone came and told you, look, the coastline was like this 5 billion years ago, and the coastline is like this today, you might ask, how do you know? Prove it to me, okay? So where you convince yourself that this coastline became like this is precisely because of the fact that the way this coastline became that is through dissipation, right? Like the sea had to come and erode the sand, okay, over long periods of time. And the point is, that slow dissipative process is still happening even today, right? So I can go to the ocean and I can look at the fact that the ocean still continues to erode my coastline, okay? Anyone who owns a home in a California beach today. And in quantum field theory, we have a similar phenomenon, which is the fact that indeed, I had to invoke these light weakly coupled axion-like fields whose job it was to change the Higgs mass over the eons of time, whose job it was to change vacuum energy over the eons of time. And those fields can still be excited today. They can still be wandering around. They'll be changing the Higgs mass in a small amount today. That could be like relaxation dark matter, as we call it. Or there's a scalar field that could still be rolling today, changing the vacuum energy ever so slightly. If it does so, you might be able to go and look for these things in the laboratory. Right? So I don't have time to tell you more about these experiments that we have in mind about how one could go after this. But this would be the way in which you actually test these things. That you look for a time-dependent Higgs mass, for example, which can be done in a number of experiments, or you look for a time-dependent vacuum energy, which can also be done through cosmological surveys, but you might also be able to look for it directly in some experiments also. So with that, let me stop. Thank you. Alassane. Yes.
And the Desi anomaly have something to do to this scalar?
Because it's a time-varying dark energy, you mean?
Because
Yeah.
now it looks like so the sign of the anomaly is like you see a cosmological constant, and next you start
Changing.
going down.
Yeah. No, I'm definitely interested in that story. I don't know observationally how robust that claim from Daisy is, but yeah, definitely. Oh, all right, everybody buys Relaxation. That's great. Thank you.